Last time we talked about recurrent neural net and LSTM. Today we will continue our discussion with sequence modeling with attention, transformers, and BERT. So here we go. Neural network architecture is very flexible. You can start with a vector-to-vector model, which is a vector input and produce a vector at an output, or you can start a vector-to-sequence architecture with taking one single vector at input and produce a sequence of vectors. And you can do sequence to vectors with taking a sequence and then produce only one vector. And finally, you can do sequence to sequence, which is taking a sequence and also output a sequence. Now, certain architecture will have its own application, so we shall visit this application. Number one is vector to sequence model. So it map a fixed length vector x to a distribution of sequence y. And this you can see it at a application to image captioning. Each element of the caption will be served both at the label for the previous time step and as input for the current time step. So here's an architecture, and it taking an image of a vector fixed length, like the image of a puppy, and through the network produce a sequence of words. So a cute yellow puppy. A sequence to vector model do quite the opposite, taking a sequence of input and output a single vector at the end of the sequence. And such network can be used to summarize a sequence and produce a label at the end. So you can think about it at a sentiment analysis or review, positive or negative. So say we have this network and we're feeding a sentence, say this content is fantastic. The network can learn to produce a softmax vector to say whether this is positive or negative. We can also do sequence to sequence model, which is also known as the encoder-decoder model, which you generate a output sequence given a input sequence. And you can think about it as an application in machine translation, right? So the hidden state of the decoder, which is up here, I'm gonna try to compute a fixed size context vector C, would represent the semantic summary of the input sequence, and then that can be used at input to the decoder to translate the words that it encoded. So for example, I study at school, translated to yo estudio en la universidad. Now, let's pay more attention with RNNs with attention mechanism, which is a special type of RNN. And the RNN with attention mechanism started with a 2014 paper by Dmitry Banganov and Joshua Bangio. I know this name keep popping up for a good reason. So the idea is to read the whole sentence or paragraph to get the context and then produce the translate word one word at a time. And as you producing the word, you focus on different part of the input sequence for the semantic details. And this attention mechanism had revolutionized machine translation and NLP, natural language processing in general. And let me explain, say you have the words in English, like this one, an agreement on the European Economic Area, blah, 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 and translate into French. Each of these words are mapped to the corresponding word in another language, and the mapping typically follow a very straightforward pattern, except for the word the European Economic Area. When translated into French, it's actually reverse. The become la, but European become European. Actually, back here, so the order reverse. You can see here the visualization, the order is reverse. So if you were able to capture this pattern or capture the semantic relationship between the word of translated sentence, you can have much more accurate translation. So the component of the attention model consists of the encoder, like you see before, which it read the input and convert into feature vector associated also with the word position in the sentence. So there is a new type of encoding happening here. And these feature vectors are going to be part of a what called a memory of semantic representation. This just it contains just a sequence of semantic representation, and from there the decoder can exploit the memory, and each science have to put attention on different content of the memories, right? Whether it's translated the word in different order. So the intuition about the attention model is quite simple, actually. It is just the weighted average. So the context vector C is formed by taking the weighted average of the encoder hidden state, HT, with the weight alpha T. And the weight alpha T's are produced or trained by the model itself by applying a softmax layer on some attention score that measure how well each input is aligned with the decoder previous hidden state. And because this weighted average is a smooth, differentiable approximation, it can be trained with backprop. However, RNNs and LSTM has some limitation that was difficult to overcome. Number one, it is very hardware intensive to train, very difficult and slow. It's not feasible still for long sequence. I know LSTMs are trained on longer sequence, but if you train LSTM on a 100-word document, the gradient gonna be produced like a 100-layer network. It's not allowed for any parallelized processing because the input data need to be passing sequentially. And finally, it doesn't have any available free train model. You always have to come up with your specific label data for every task. If only if we have a free train network that can utilize parallelizations for long sequential data and use the attention mechanism. Is it too much to ask? Fortunately, that is what we have with the transformer architectures. So what is transformer? No, not these transformers. Transformer is the next big thing for now. In 2017, there is a groundbreaking paper, Attention is All You Need, by a team of Google researchers to take attention mechanism idea and create an architecture called transformer. And the transformer architecture turned out to be much faster to train and easier to parallel, as we shall see soon. Then the transformer has significantly improved the state of the art in natural language processing without using any recurrent or convolutional layers, only just attention mechanism. Apparently, attention is all you need. And so, as sequence modeling problem go, we go from backs of words to RNN, LSTM, now to transformer. So let me do a demo on writing with transformers, right? And you can see there is a sentence that I already write here, but let's start something new. So, start with this. I can say, as you are watching this lectures on sequence modeling, and now what I'm doing, I'm gonna let the machine to finish my paragraph. Isn't that great? So I just press tab, and I'm gonna choosing the next sentence, and keep introduce new words, and it to keep writing by itself. And I have no choice, I just keep picking the first word. But you can see here, it's actually formed sentence very, very well. So I can keep writing this, but you do see the points here. Given just the context that I type in the few words, it can actually generate content continuously. You might as well try to write a novel using this transformer method. But you can play with it absolutely later on. But let's go back to our presentations here. So it's pretty cool. It can generate the entire sequence. How is it actually working? So here's, let me introduce you to transformer architectures, which is a very complicated architectures. And we're going to look into that piece by piece. So first, we're going to have a encoder, just like our RNN with attention. And the encoder take in input at the batch of sequence of words. It will decode each word into the embeddings. So this is a 512 dimension embeddings at using with globs or word to vec. And then it's also stack n time. So these are layer after layer of attention. I think the original paper used 6 layer of decoder encoder total. And so, for example, the word I study at school can be translated into embeddings just at this, except instead of 3 blocks here, it's actually 512 blocks, right? Of course, I'm not gonna write 512 blocks on the slide, so I'll think about it at the very deep, high dimensional data. We also have a decoder at the right-hand side. When the decoder taking target sentence at input, ship it one time step for the reasons that you need to only see the previous time step and not the current time step. So yeah, you ship right for one time step. You receive the output from the encoder. You need some information from the encoder, and you also stack n time in the paper 6 times. And it's output the probability of its possible words once every time step. So let's dig deep into the encoder here. And you can see here, I'm focused on the part of the encoder that do positional encoding. So this is a new novel thing that they add in. So think about positional encoding is the way you can add position of the words into your embeddings, right? So you have, beside the regular embeddings, you now have the position encoding or embeddings, right? And since you adding them together, you had to figure out the way to get the dimension to match well. So the positional encoding or embedding simply just a dense vector had the same dimension as the word embedding that represent the position of the word in the sentence, right? So you can think about position of the word in the sentence at a single number, but how do you represent it in 512 dimensional space? And the trick here is to use sine and cosine function. So you can compute the matrix positional encoder PE with P row and I columns, where P is the word position in the sentence and I is the embedding dimension. And you can use this sine and cosine formulation to it, which depends on P divided by 10,000 here is presumably the size of the dictionary, powered by 2I divided by D. And if you notice here, all of the even columns are here and the odd columns are here. So the signs are calculated in the even column and the cosine in the odd columns. At the result, here's an example of the positional encoding. The row is each word, so these are 20 words, and the columns are the dimensions, you see the 512. And you can see they kind of split in the middle because the sine and cosine taking separate parts of this dimensions, and you can see that it trying to produce a 512 dimensional position related data, because this is calculated upon the positions that can match the word embeddings dimension. Okay, so you're gonna add that position encoding into your word embedding so far. Okay, let's continue. Next, we're going to talk about inside the block. It's called the multi-head attention. But before we talk about that, let's talk about cell attention for a second here. So consider this sentence. The animal didn't cross the street because it were too tired. Okay, seem like harmless sentence, but if you looking at this, you can study how different words in this sentence actually related to each other. Or say, for example, the word it here, how is it related to all the word in its own sentence, right? So for the word it here is very much, you should pay attention to the word the and animals, right? Because that's obviously what it is. But you also had to maintain some sort of attention to all other words in the sentence. So the idea here is for every sentence, you should pay attention to all of the word in the sentence and kind of maintain some sort of a self-attention score for each word. The nice thing about this is that so that you know what it's referred to inside your sequence. And then you a sentence here, but you can think about this. It depends on the window that you include in your sequence. This could be a very large window that you consider, right? So keep that in mind. You go to calculate the cell attention score. Right. So we're gonna compute the cell attention score with query, key, and value, and these are inspired from the information retrieval system. Right. You have a query to a paired key value. Right. And for every encoded words, we're gonna generate a key value pair as well as a query. Right. So we're gonna generate three things here. And the cell attention score is a product or the inner dot product of query and key. All right, so for every word here, for example, I study at school. For the word I have the positional encoding. Then from here, I generate query, key, and value. So I do that for each and every word. Right? So how do I generate it? Of course, I'm going to have a weight matrix to generate these query, key, and value matrix. So here I have a matrix WQ. So here that I combine all the words together into a matrix, right? So I do a matrix multiplication here, but these are the weight that associated with the query, WQ, to get query. And notice in the queries, I have query for different words. So each of these queries break down by different words. Each word is a row here, right? So I have queries, key, and value, and these gonna be what I'm gonna use to compute my attention score. Now notice all of these weight can be learned by backpropagation. So these are the parameter of the network that I want to learn. But let me see what I can do with this query, key, and value, okay? So we're gonna build some one-to-one comparison. So we basically build the cell attention by comparing each word to every other words in the sequence, okay? So for the word I, my query gonna be I, right? For the word I. And then I use the dot product between query and key. So I time the query of I, which is the same throughout here, inner product with the key. So the key from different words. And each of these dot product gonna return a single number. That is my attention score, right? And from the score, I can apply softmax to make it into the probabilistic distribution. So you can see it here. I and I very much relate to itself. 92% to itself, 5% to study, not much to at school, right? And then what I'll do is I also have a value vector. See if I can relate the score to its own value, right? So I multiply the softmax to the value, and then I will sum this up, all of these values up, to a what called a context vectors for the word I. Okay, so these are the context vector that we might be able to see later on. So I'll do that for all of the words in my sequence. And the nice thing about this process is they are independent, so you can parallelize it using parallelization, right? So for study, for example, study are pretty much very related to study. I had to look at study, pay attention to study, but study also related to school. So you can see the words here, it's 25% related to school. So this, when I look at study, I also need to look at school, right? And so it encapsulates into this context vectors. Same with at and school, right? Notice school related to school 70% of the time, and it's also related to study 27% of the time. So from this context vector, I can concatenate it to get a context matrix. And that's what I'm going to use to my next state, right? Now, because this is a multi-headed attention, what I'm seeing now is not only I generate a single attention matrix using this set of weight on a query, key, and value, but I actually gonna do this multiple times, right? So I can generate one set, one matrix. I can generate another set of attention, another matrix, so on and so forth. What happened here is all of this process also can be done in parallels. So I'm taking full advantage of my parallelism to make the process as fast as possible. So after you generate this, you can concatenate it to a single big matrix. And notice, because if you concatenate different matrix, it might not have the same size at the original encoding. So what I'm gonna do next, I'm gonna try to map it back to the original encoding size by multiplying it by some weight WO, and WO is also a learn matrix. through backprop. So with that, I get back my original size of the encoding positions and so on. And I also be clever about this is that because the backprop here might lose a lot of position related information, what I'll do, I make a residual skip pass to pass the position information forward, just like the ResNet. Right? And up here, after the layer normalization, which I will not go into details here, they have their own paper about it. After the normalization, I'm going to feed it into a feed-forward network and then do again normalization and then pass the signal forwards again. So notice that my output at the end of this pipeline is the same as the original input. So this is a very crucial point. If I was able to do this, I can repeat the whole process over and over again. So that's why this encoding layer can happen n times here. Right? So with input, I can keep passing again through itself 6 times with the original paper and get a same size matrix here. It's called the context matrix here. So what I'm going to do with this context matrix, I'm going to use it for the encoder-decoder attention mechanism. So this is slightly different from the attention mechanism of cell attention, right? And this is different in a way that you can look at it. The query was actually created not by itself, but from the decoder cell attention mechanism, right? So this, you can see this come in here, this query. But the key and the value matrix is going to generate it from the encoder stacks. So remember that WK and WV, you're actually going to use that to feeding into this mechanisms here. You're going to feed the key and value matrices into this, right? So similar to down here, if you take 3 input, query, value, key, you have this right here, right? So the idea here is to help the decoder to focus into appropriate places in the input sequence. That's why we learned the context matrix for, right? So the attention mechanism here help it focus attention on the input sequence. Okay, and for the decoder, I can again stack it n time. The paper stack is 6 times to learn multiple representations of the decoding. Right, so here I go, and the decoder final output can be passed to every single layer of this decoder. Okay, so you notice there is one thing different about the decoder is the multi-head attention now is masked. Why is it need to be masked, right? The idea here is that for the decoder, which you look at input data, you cannot see the future, right? So you have to mask during training all of the sequence that come from the future. And the way we do this is, well, let me explain it a little bit better. So say if the word is start, I am fine. By the time you hit the word I, you don't have access to the am or fine. So what happened is you had to block this 2 out from view by masking it, right? By the time you get to am, you don't have access to phi. But when the time you get to phi, you get access to all the word that previous before that. So the idea here, you not peek into the future, because that would be cheating, right? So you have to mask this to your network. And the way you mask it is that you have a scale score, attention score here. You're going to build a mask, which is very simple because this is just the upper half of the matrix going to be set to negative infinity. And then when you add it together, they all negative infinity on top half. And when you do softmax, these are all 0 score. It's that simple, right? So you don't peek at the words from the future. Okay, now let's look at the output layers, which is after everything's go through. You have several decoding layers here, and you have the output from the encoding layer feeding to it, basically a sentence that you need to translate. And you start with a start sequence. So it's gonna pass through your network, go through a linear function, and then the softmax to get the probabilities, right? And you pick the highest probability, maybe this one. And this softmax layer is gonna have the same length at your dictionary, which in this case may be 30,000 words in Spanish or so. But the word yo having the highest probability. And then what happened is you take this one and you pass back into the input. So yo now it become an input, and you use that, go through the whole process again, and maybe now the word, because of your encoding output here, the highest probability will be a studio, and you feed a studio into the output, and then you go, the next word, and you feed it back in, so on and so forth, until you hit the end of the sequence. So the end is also a token within these vectors, right? So that is how you basically translate a sentence using attention and transformer architectures, right? So what is the property of transformers? Right? It sounds very complicated. The awesome property of transformer is that it does not suffer from short-term memory at all. It have infinite reference windows. So you can see the entire context of the sequence. And even though it have auto-on comparison, which is the n square where n is the sequence length, it doesn't seem that bad, because you can parallelize the entire comparison to speed up training. So it use parallelism to help a lot. And every output is a weighted sum of every input. And the weight that you use is a learn function. And you can use backprop just like any other neural net. And because of this architectures, the NLP industry had achieved unprecedented results. Now, the question of the transformer for the decoder is how to map the semantic context. Asking the question, what is English? What is the context here? Whether the question of the decoder is to how to map word from one language to another. But really, both eventual goal of these decoder and encoder is ask the questions, what is language? And that's a very hard question, right? We have over 200 languages spoken in the world. What is language? And the attempt have been made by stacking transformer encoder together. So you have an encoder here. I'm going to keep stacking it together for a long sequence of layers. And that gives rise to idea of bidirectional encoder representation from transformer, or BERT. Well, not this BERT. So what is BERT? BERT is a large transformer match language model. It is a language model because it is a free-train statistical model to predict the probability of sentence or phrase. Sound pretty good. Why is it masked? Because it's a kind of contextual word embedding that can be used at input embeddings, and masking also one of the way that you train it. It is a transformer base, which is a family of neural network that based on attention. And finally, it is large. It is 24 layers of encoding, 120,024 nodes, 16 attention head, and 340 million parameters. And by the way, when it would train in the Wikitext dataset, it trained on 16 TPUs at Google and take a full 4 days to train. So they would, don't try this at home. Right? Okay, so what is the BERT application? It can solve more tasks than the regular transformer. Not only it can do neural translation, it can also do question answering, so like Watson, semantic analysis, text summarizations, and BERT basically attempted to understand language. Way to go, BERT. So BERT had two phrase training. Number one is free train to trying to understand language. And number two, a fine-tune to a specific task. So you can see transfer learning here at work. So free training. BERT trained on the Wikitext dataset with 100 million tokens, extracted from a set of good and featured article on Wikipedia. And here's example of the input. Not only taking input at words, they also take metadata, and there's several metadata here that you can see. Number one is the token embedding. You embedded a COS token at the beginning, This is called sentence classification. A separator token at the end of each sentence. You also have segment embedding, which is a marker to distinguish one sentence from another sentence. And also positional encoding, which is the encoding that indicate the position of each word in the sequence. All right, so there are two things that BERT trying to learn during the free training process. Number one is match language modeling, or MLM. So what happened is that it's going to try to mask out 15% of the word under some mask token, and then use supervised learning to predict only the masked word using the context of non-masked words. So an example would be that you given a sentence with some words masked out, and BERT would trying to train to predict these masked out words, right? And they have some technique to avoid modeling only trying to predict the mask token by having 10% of the total mask token replacing with the random one, while the other 10% are left unchanged, which is the original words. So at the result, it was able to predict some mask word. And you can think about this because it's done randomly, it can generate basically lots and lot more training data to learn these mask words. Right? So it kind of train almost supervised learning, but these are more self-supervised learning here. The next way it does it is using next sentence prediction. So not only BERT trying to predict the next word, BERT actually trying to predict the entire sentence. And in order to do this, it needs to understand the relationship between sentences separated by a sep token. So BERT trying to determine whether the next sentence given a sentence with mass. Right? Again, use self-supervised learning, feeding 2 sentences at a time, and 50% of the time, the second sentence actually come from the first one, positive example, and the 50%, the second sentence are a random pull from the large corpus, which is a negative example. So in an example, feeding 2 sentences here, BERT gonna have to classify whether this second sentence is after the first sentence, which is index, or is it not, right? So this one, obviously, it belong together. This one, the man to the store, penguin, a flightless bird. So definitely not next, right? So BERT trying to identify whether this is next or not next. So that's the free train. How to fine tune BERT after you get the free train model, right? So after the free train model, all you have to do add a single top layer on top of the core model for your specific task. And what do? It depends on your application. Here we use the question answering task. So upon receiving a question input, the goal is to identify the right answer from some large corpus. So the whole goal is trying to learn 2 extra vectors, start and end, to mark the beginning and the end of the answers. Right. So I would have some input questions. Where do water droplets collide with ice crystals to form precipitation? And the input paragraph here is blah, 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 blah within a cloud. So you want to train this soft max layers here to know where to start the answer and where to end it. So the output answer should be within a cloud here. But you only need to train the top layer because BERT is very powerful free train language model already. Okay. Now, how do you do that in 12 line of code, right? So first thing you do is that you can load the free train BERT model. In this case, I have a particular free train model from the BERT base case, right? Oh, not to mention you had to set the tokenizer, which is, you transfer from the string to a token. You loading the free train model and you loading your data set as well. In this case, my data set is from the Microsoft Research Paraphrase corpus data set. So next, you use the same operation at the dataset class that we've seen before in handling large data set. And then you use a very similar setup at neural net. You set up the optimizer, loss function, the metrics, and put it together. And finally, you call fit. That's it. BERT do have some benefit and drawback. Number one benefit is it's a transfer model, so you can use it for any kind of specific tasks. It have success with fine tuning. If you were able to fine tune, it's very good accuracy. The pre-trained BERT model available in over 100 languages, but it does has some negative as well. It's big and slow to train. But hey, you have the free train model. Training in the last layer it does still take time, but it's not that bad. It is expensive. Well, only if you want to train it from scratch. And finally, this is the big one. Need to be fine-tuned for downstream tasks, and depending on the task you have, this can be finicky. But what can you ask for? It's very, very cool model. So in summary, we have a transfer learning that works, right? Free train model can be used for fine-tune new tasks. And this is one particularly make me very exciting because back in my graduate school, that was I was focusing on transfer learning for some application in image processing. So transfer learning works. The attention mechanism have revolutionized machine translation and NLP. Transformer and BERTs are easy to train, more efficient neural net. So for NLP model, we go from bad words with an ancient time to RNNs, LSTM, to transformers, and now to BERT. Who know what's gonna be next in the few years? Very exciting part of research. And for neat tool and NLP, I encourage you to check out, besides TensorFlow, Keras of course, Hugging Face project, which include here in this link for pretty cool project, right? I know we cover a lot. This is quite a long video, but I think it's totally worth it. These are state-of-the-art neural net at this time, so very exciting stuff. But next, we're gonna also cover even more exciting stuff with generative learning. So see you in next module and videos.